Welcome, everyone. Welcome to our kickoff for 2026. This is our first meetup, and we're looking to a great 2026 to bring more AI, data engineering, and web development platforms. But I'm glad to have you here with us today. So let's get started. Today's presentation is called the Cognitive Data Lakehouse. And basically, as you do data engineering work, we try to build out what's called a data lake and integrate that into a data warehouse. And that seamless integration is what's called a lakehouse. So it enables us to be able to query information, integrate information into the data warehouse from the data lake in a way that it does not require any type of ETL process. And that's what we call a zero ETL environment. But with that, there are many challenges, right? Whenever we bring data into a data lake, we usually bring that data in a raw data format. So it's usually some kind of comma separated file or tab separated file, or it could be data streaming as well. But the point of a data lake is to sort of aggregate the data from different sources, so we don't have any control over the schema of those sources, right? So the fields could be different, the names could be completely different, the data types are completely different. So in today's presentation, we want to take on that challenge of a zero ETL environment and see how we can leverage AI to help us basically assist us in building out and overcoming some of these challenges. So welcome, my name is Oscar Garcia, and I have background on web and data engineering. I love building and playing with new technology so I can share it with you, with the community. I'm also an author. I published a data engineering process fundamentals book, and that book basically takes us on a process-oriented venture or journey to be able to build out a complete data engineering solution on the cloud. And you can have all the codes, examples, files, Jupyter notebooks, and scripts on a GitHub repo. So if you're interested, just scan the QR code and it will take you to some of those repos, in addition to data engineering, AI repos, and web development repos. So glad to have you here today. So let's get going. So we start with phase one, zero ETL strategy, right? And I cover a little bit of that already. And basically, the whole purpose of that is to be able to bring data without having to do jobs, right? Without having to process the information and actually load it into the data warehouse tables. That's the end goal of that. So how do we do that? Okay, so the purpose here is to leverage the data lake and receive information, whether it's JSON, CSVs, or data streams, into our data lake, right? So the raw files remains in the data lake, and we don't really worry about replication of data. And what that means, basically, we don't worry about getting and processing the data in real time or in a batch process and move it into the data warehouse in materialized tables, right? So how does that work? How can we have all these files on our data lake and be able to leverage that information from our data warehouse? So that's what's called the virtual access. And that the entire purpose of this is to be able to build external tables that actually query this information from the data lake and it actually projects that information as if it was a real table on the data warehouse. So the purpose here, or the goal here, is to use external tables. So every time you have a data source, for example, with multiple files, you can basically create external tables using patterns to be able to say, for example, select all the files from a particular state or a region or so on, and be able to bring all that information and project that information into an external table. And the whole goal here is that it reduces the cost. So if you work in cloud engineering, everything has a cost, bandwidth, processing power, storage, and so on. But the storage on a data lake is a lot cheaper than the storage from a data warehouse, right? And also the ability of the technology to advance in such a way that the latency issues are no longer a big problem, right? You can actually query data from a data lake and the performance is pretty acceptable. So the goal here is that we get the data into our data lake and we view the data from external tables without really ingesting that into physical tables. And that is the story for what we call now the data lakehouse. So zero data replication means now is that because we have the ability to have external tables, we can now extend that by creating views, right? So instead of us creating a process that brings that data from an external table and it materializes that into a physical table, we are able to create views that read that external table information and can handle all the transformation that we need. So for example, usually when we consume CSV files, the datetime field, maybe the format could be something that is not acceptable by the data warehouse system, right? So we'll cast it to a datetime, we'll pre-format it, and we'll do that for other fields. So for example, we'll cast to integers, to numeric, which is amount of money, for example, and we'll do the transformation and the casting and the naming conventions, right? So if you have standards and naming conventions, maybe you want all lowercase, field names and so on, that's where you do it. So if you go back and remember, an ETL process does that for you, but it does it with, depending on how you're doing it, you could be doing it through Python code where you're processing the data, processing the fields, transforming them, or you could be doing with SQL. If you're doing SQL batch process, you do exactly the same way. And then eventually you move it from, from raw source, usually a table that has no constraints, everything is string, text, what have you. And then you transform it into a physical table, you materialize it into a physical table that has the right data types, the right index information, clusters, and so on. But with this approach, we don't do that. We actually do the process and the data transformation into views, and we're never materializing anything into a table. The cost reduction there is huge. Excuse me. So, and if you're familiar with the medallion architecture, this is really what's called the bronze zone of the medallion architecture, which is really you're staging your external data sources into a layer, which is the staging layer, which is basically this view. And that's really what the zero data replication concept is. So at this point, you do not have any type of data storage cost for this. All right. So now we understand the lakehouse. We understand we're getting data from external sources, from a data lake. But what are the challenges, right? So the challenges basically, as we get multiple data sources, right, we're going to have what's called schema friction, right? The field names are different. The naming conventions are completely different depending on the source, right? You have no control of that. Examples are, you can have something called device number, or excuse me, device NO, right, which stands for the same thing, but you see the difference in the field name. So the problem with having a schema friction is that, for example, if I move a file that has device number, right, and it's, for example, a string, and I have another source that for some reason the ordering and the names of the fields, the names of the fields at that point are not that important because we're going to do transformation and naming conventions on the views. But let's say device number is moved to another location, another column. Instead of column 1, is column 5, for example, right? Which is called now entity drift, right? The sequence, the order of the fields is different. The schema it changes because now you're really not matching on the field on the column location, right? Position, I should say position. So basically what happens here, one of the shortcomings of this is that as we create this CSV, we're mapping to that CSV and we create all the field names based on that, but we have no control. If another CSV comes in and is different, then that will break your that can break your external table, right? So, and we'll see how we can resolve that, the patterns to resolve that, but those are the challenges, right? You have entity drift, a new CSV came in and it broke it, right? So how do we deal with that? How do we control the different schema versions to be able to avoid that? And of course, type mismatches. If, for example, our external table is looking for an integer for the device number, let's say the device number is 950, right? But a new feed brings device numbers that are alphanumeric, and that device number now is D950. That's going to be a mismatch, and that will definitely also break your schema. So that's where we spend a lot of time when it comes to data engineering. We need to start maintaining all those differences and dealing with those things, right? So the question is, how do we improve this? How do we handle this other than doing it manually, right? So this is where we introduce AI, right? And AI, I'm sure everybody has been using it, whether through the browser or some type of API integration and what have you. So the challenge is, how do we use it for data engineering purposes? Because to me, that has been a shortcoming, right? That I would like to be able to, from AI, be able to say, look, I got this schema definition. I want to create a view or something to transform these fields, right? I would like to have an integrated mechanism to be able to do that, as opposed to bringing that information, capturing the schema definition and maybe putting it into a chat, AI chat, to be able to do the transformation, right? So that copy and pasting is sort of difficult, is troublesome, is slow. So how do we leverage that in today's data engineering world? So a lot of data warehouses, we're going to take BigQuery as an example, but a lot of the warehouses now are tightly integrated with AI. So how do they do that? Okay. But let's first talk about what is it that it can do. So if you remember, if you're familiar with database systems, right, they have a lot of metadata. Completely everything is metadata, right? You can actually query some system tables that would tell you, you can say, give me the catalog information for this table, and it will give you all the field names, cluster definitions, and so on, right? It will give you all the information. So if you think about that, this is very important. This is what enables AI model to be able to understand your tables, your views, your system. So that becomes part of the prompt for AI. So that this is important. So this is what we can leverage to be able to do DDLs or SQL logic or data analysis, right? But the key is, how does it work? How do we make it work in a way that is integrated into a database or data warehouse? So so there is the concept now of remote AI registration. And basically what that is, it enables us to be able to, within the SQL, create models. So we can say, hey, create this model with this connection, right? And what that is basically is tightly integrating behind the scenes, under the hood. It's integrating an endpoint to a AI model. So so it appears as if it is tightly integrated with the system, right? And it is, right? It's really creating API calls into an AI model to be able to do something you need to do, right? So as you register that model into the data warehouse, now we can leverage it by actually querying the model definition. So here you can take a look at how we do remote registration. And also you can look at how we do the automated inference, right? So basically here we're saying, hey, a quick example is, hey, let's use this model, which we register, and generate text based on, and we give the prompt. If you're familiar with that, always give the AI model a prompt to be able to tell it what it needs to do. So here we're saying, hey, compare source A and B schemas and what have you, right? So basically what that does now, at the moment you're saying, hey, compare the schemas, the schema definition, the metadata for that is available to it, because it will go in, of course, because of the integration with the data warehouse, it will query the catalog information from the system and say, hey, give me whatever table A is, table B is, and it will build out the prompt. It will enhance the prompt for you. So it is acting as a SQL agent for you, AI SQL agent, right? So it's actually building out your prompt with information for metadata from the data warehouse and building out a prompt that's going to help you build what you need to do. Whether it's maybe here you're looking at a schema drift and you're saying, hey, compare these two sources and unify them. And it may tell you, hey, we can because we have a drift. The source A has 10 columns, B has 12. There is a drift. Something is different. We can't really unify them unless we dropped something, okay, or unless we have data type mismatches and so on. So at that point, it's going to enable you to identify that quickly. And this is where we call the schema discovery, right? So as an example, just to make it more concrete and realistic, we can, in our example, we're going to process telemetry data from multiple manufacturing locations and unify the information for control processes and analysis. Okay, if you're not sure what that means, basically what we are saying is there's going to be some kind of data feed that's going to go into our data lake. It involves multiple manufacturing locations. And the challenge with that is, as we discussed, is we have schema drift, the files are different, and we need to be able to unify this information because we want to execute control processes and data analysis in all the manufacturing locations, not just one, right? And don't worry if you're not familiar with that industry, but this applies to all the different industries. But to make it concrete, for now, we're going to be using, for example, we're going to, first of all, generate the data definition language for external tables by pointing to a compressed data feed that is in the data lake. And basically, what we're going to tell AI is we're going to ask the model, hey, create an external table using this data lake path. So if you see that GS factory DL, that's the URL to the files on the data lake. And you see the pattern, that asterisk basically saying, pick up anything that has this shape, this pattern, right? Telemetry, something. And that is for a particular device. And you can open that up to all the devices if you want, or you can just make it concrete to a specific device. It really involves on the understanding of your data definition to see what you're trying to achieve. But the point here is that this fits into any of those models. And you can say, I got this file. I want to create an external table. I want you to build it with these options, which is handle compression, skip the one row, number one row, because it's the headers, and infer and add the schema using lowercase. So it's going to infer based on that definition of that file, because it's going to go get the data. It's going to go get it and analyze the data and say, okay, I see what it has. Let me go ahead and build out a external table that's going to match whatever I'm finding. So at that point, it's going to generate the DDL, right? And this is what it looks like. it's going to say to create or replace an external table for this particular data set in this table name, external table name, right? So it's using device number, bay ID, and so on, right? And you can see the options, the patterns, the path to the files, and all that. So what that means is, the moment we have this external table, and basically we add one file, we can query that table for that file, and we add another file, and then another, and so on, and we start adding multiple files, let's say for a window of an hour, let's say. So let's say it's an hourly file that we're getting, because telemetry data for manufacturing devices, there are usually robots. They're sending thousands of records a minute, right? So it's huge amount of data. So so we're able to, that external table, you'll be able to query. So there's to query that particular file if you want. So basically, there is metadata associated with that, and you can actually say, I want the file for 3 o'clock in the afternoon, right? There's a source file parameter there that you can say query for that, and then you project that into your views, and you can query based on that, and you can go very granular into that. But that's just normal data engineering capabilities. The point here is that with AI, I can actually say, build me these external tables with these definitions, right? With these options. So now this is basically the same. So, but if you notice, I'm gonna go slower here. If you notice, we're loading the US factory here. So this is the US factory that we're loading for some device 540. And then we're moving on to building or getting the Mexican, the factory from Mexico for device 940. But it's the same thing, but it's different, right? So usually what's going to happen in your data lake, you're probably going to create different folders for different sources, right? So you're going to say, I want the Mexico files, I want the US files, and I want them now, I want to break them down into a device, right? And you want to associate those device names. And the idea behind that is because this has a lot to do with governance. So think about data governance on that from that perspective, and it will enable you to add policies that you can say, hey, we decommissioned this device 940, that data is no longer needed, we can archive it, right? So it enables you to have control, governance over all the files, because eventually there's going to be so many files that you have to have policies to clean that up. But what we're saying here is, yes, go ahead and build this out. Give me the Mexican table definition. All right. All right. So, okay. So now what we did is, from the data lake, and we built our lake house. We have our data warehouse integrated with our data lake, and we can see the files, right? But the files are different. There's schema drift. The data types are different. We need to start. We need to actually now build a layer, the view layer, that enables us now to do and execute transformations, typecasting, right? And do all those things that are going to need it for us to normalize the information that we're consuming. So this is where we can actually use AI as well. So through the model that we register on our data warehouse, we can actually go ahead and say, okay, create me a view from using this view name, and we're using our naming conventions, and we're passing our data sets. Our data set in BigQuery is like a data warehouse, right? Or like an alias that it enables you to do a namespace definition. But that's how basically you can break down the different databases into BigQuery, right? So we can ask the model, hey, build this out for me for the US telemetry data. Select all the columns. Use that USA telemetry table, which is our external table. Safecast the created column as datetime. So basically what we're saying here is, because from the external table, everything comes in as a string, we can actually now safecast that to datetime and be able to to generate, to safely cast and transform the information as we need it. So what AI is going to generate is going to output a string, a text that's going to say this is the DDL for that, and it gives us the create or replace view with the name, with the field names, with the source, and so on. So at this point, what we're building out is the view layer. We're actually now saying, now let's do our transformation, right, into our view. So we're actually doing this in real time without any ETL process, right? So now the challenge is that we do that for US, we do that for Mexico, and so on, because the models are completely different. But we want to have a unification. We want to be able to say, we want to be able to go from one source and say, hey, give me, I want to do analysis on all the systems. So we need to do a unification of the data. And at that point, that's another manual task that we have to code a lot of the views to be able to do this. And we can leverage AI to help us. So now we can tell AI, hey, let's go ahead and consume these views that we built, and let's go ahead and generate a unified view, right? So here we tell it, hey, create this view telemetry that creates a union of all the fields from the different views, right? From in the different regions that we have, which is US, Mexico. List out all the field names, never use asterisk for field names, because for unions, we want to be able to be very explicit. So we protect from schema drift, from the problem of data changing, adding a new field, and so on, and breaking our process, basically. In the unified view, it's a simple union all, where we actually get all the information together, and we basically unify this data, right? And this is the place, of course, that this only unifies information. So every other view, like the US telemetry, Mexico telemetry, and so on, takes care of the transformation for that region, right? Takes care of the typecasting and the transformation and so on. And normalizes the data, establishes naming conventions, so the unification is simpler. But the thing is, because we already provided that information, the metadata of the data warehouse is read by AI, and AI is able to discover that and create those views for us. But then we continue to scale this out and continue to grow in another manufacturing region or location is added to our universal system. And we now, with our challenges, we need to add the China fee for our manufacturing plants in China. So, okay, so we do the same process. We go and tell AI, hey, AI, we have a new fee. This is the location. Please create our external table definition, create our new views, right? And all that code is generated. And of course, somebody has to review and publish that. But then we get into the DevOps loop, right? So now we're in production, we're reading all these views, we're creating dashboards and so on. And we don't want to just introduce an entire new feed into our system, right? So even though AI is enabling us to create the code for it, we definitely need to make sure that this code is not going to break anything. So we can definitely use AI to say, create the new feed, right? Hey, create a new feed. We have a new external telemetry source. Update our unified view to include this new data set, right? And then that has to be reviewed, and that has to go through a DevOps process where we ensure that the information is production quality, and we're able to apply the unified changes and push this to production. Okay, but is AI just good for DDLs or simple queries? The power of AI really shines when we start doing data analysis and we start doing advanced data detection for anomalies, and in this case, for this industry, out of control conditions. So just let me give you a little bit of background on this. So the whole purpose of capturing telemetry from all these devices, from all these robots, is because they are working like robots, like machines, and they're producing tons and tons of telemetry data, right, a minute. So they're saying, for example, they're measuring. They did a step, they are measuring for quality, and they're sending all this information, right? But this quality, this information can deviate, right? So there's the concept of a control limits, and control limits basically establishes that, to simplify, that a process cannot produce a reading that goes beyond boundaries like 8 and 2, for example. This very simple boundary. So of course, 8 and 2, you cannot go out of control there. So if you go below or over that, that's an out of control condition. What that means is that as the robots are producing information, they're taking readings from whatever it is that they are building, and they measure those readings, and those readings are inside that boundary, which is either 8 or below 2, and we can measure that. So AI is excellent for that. AI is very good at doing any kind of data analysis where we can actually ask and say, hey, build me an analysis for an SPC, which is a statistical process control, which is to measure the data, and do root cause analysis. Please generate the SQL using this data. So now here's where we can actually, AI is very good at it, because it's going to go get that telemetry, that metadata for those views. And it's excellent at creating this, right? Because this is very concrete. This is very concrete information and science, statistical analysis, and it'll be able to generate this kind of views for you. And this basically what it's doing is saying, hey, I need to query this sampling of data from this particular view or table, and give me readings where there is an out of control condition. And what that it does basically in this type of process, it signals to the engineers that there's basically a problem, right? So the process is broken or is tending towards breaking, right? So you can see anomalies where you're saying, hey, in the last 20 or so readings, is trending out of control, right? It's going out of bounds. So there is an adjustment problem, or there is a defect on the parts or something. So let's try to fix that. Stop the processing, because this is an early signal, right? Stop the processing of that, because it costs. There's money in processing time, in parts, and so on. So this is what control engineers use to be able to detect problems. But to help you, but from the standpoint of data engineering, we look at the SQL that generates this data. But from a realistic point of view, the engineers basically look at something like this. This is really what that generates for them. And you can actually ask AI, give me that SQL, and it will generate that SQL for you. And then data warehouses now are integrating with notebooks. If you're familiar with Jupyter notebooks, you can leverage Python, and you can actually connect to data warehouse or database, and you can create charts. You can control graphs and do analysis with that. But just to give you some more background on this SPC, this is an SPC. And in this case, what is showing is that this process is pretty decent within the control boundaries, right? The upper limits and lower limits are the red lines, and you can see that the control is actually moving towards inside the average line, right? So this tells you it's a healthy process. It's going to deviate a little bit because it's never perfect, but it's within the thresholds the quality engineers have established for this process. Okay, and this applies to anything, right? This applies to any type of process. This is just showing you this something more realistic, but this could be associated to process, to sales, to quality of customer service and so on. But it just shows you the capability of how this integration is powerful, especially for this industry. AI is just a game changer. All right. So the advantage, right? So what are the advantages? So we talked about having to do this manually if we don't have AI. So, but it's the metric, for example, is unification speed. And what that is, us doing the work manually, right? We got to look at the sources. We got to look at maybe we look at the files. We open the files with the Excel or some program, or we use Python, and we load the files, and we can look at the schema and do everything we need to do. So we need to do discovery on that. So that takes time, right? That takes time to do that. It involves a developer, a data engineer to be able to do that. But with AI, basically, the file can arrive. We can just create a data lake location, and we can actually tell AI, hey, look, go get this file and build me a external table, and it would just build that schema definition for you, which may not be 100% of what you want, right? It will infer the names based on headers. It will try to infer some of the numbers, but maybe everything else will be string, and you don't want string, you want datetime. So that is part of your, when you start building the views to do your transformation and your standardization, that's when you will do that. But it's completely, it makes you work a lot faster, because this is a constant effort for us to be able to start consuming new data. New data is just takes a lot of time. Schema drift. So so basically we need to make sure, oh, okay, so a new file came in, it broke the previous schema, we need to create a new version. So what the process to do that is we create a different external table, let's say V2, to load that, and AI can do that faster, right? So AI can say immediately, hey, I analyzed that the file is different. And then you can say, okay, create a new file based on the new and call it V2. And that now you're going to have US version 1, US version 2, and so on. So that's the approach, that's the pattern to deal with a lot of schema drift. But AI can build that for us much faster. Definitely cost. So when we do this stuff, we need to think about data governance, and part of that is cost, right? What is the cost of doing this and running this? And definitely when we do manual data engineering and we do data redundancy, so we're basically building out everything that is in the data lake, we're moving it via ETLs into the data warehouse, and we're materializing that data into tables, and that cost of that is a lot higher than just using the data lake. So definitely data redundancy is a cost issue that we're trying to solve. And that doesn't require AI per se. That's just really the pattern. But what AI does, it helps us building the views, the table, the external tables to manage this better. And with AI, definitely, we don't have to be coding all of that. So that's everything is in place on the Google Cloud or whatever data lake you are using. But then when you talk to management and they tell you, so what is the cost of this? Then you have to be able to say the ROI is basically the velocity of the insights that we can produce divided by the cost of data and the labor of hours. If you apply that math based on in the speed that you're gaining and the movement of cost of data and how long does it take a developer, you can calculate the ROI and you can provide that to management, and you can see that the gain is humongous, right? And that's what any business wants to see and hear. So final thoughts about this basically is that we do have a lot of data engineering legacy or current challenges because most of us are still not leveraging AI, but we have the problem of ETLs breaking. Redundant storage for processed data is a cost, is huge cost for data warehouses hosted in the cloud. Hard coding, everybody's doing their own hard coding differently. So there's so many things that takes time for us to develop. So time to insights to actually build a dashboard or something takes a lot longer. So with AI, we can basically eliminate ETL altogether. We can infer some of the data, which is some of the heavy lifting that we do. Create this view, create this external table, right, and so on. And we can adapt to many other models, sources from different locations: USA, Mexico, China, and so on. And basically, this enables us to, in a faster, more controlled approach or process, be able to build out our data engineering solutions. So that is our final thoughts. Any question, Carol? I'm also on YouTube, so I'm waiting for any questions there. I hope you found this presentation insightful, and it's just perspective on the capabilities on what we can do. Let me know if you have any questions. All right. So I hope. Oh, don't worry, Carol. I also work on web. I used React, but I always done a lot of data engineering. So lately I've been doing a lot more data engineering and AI. But what you have to think about once you start working with data, that these challenges become real. And that's how you leverage AI for this. And of course, you can do a lot of AI for web, right? You can build controls and you can say, hey, build me a React component to do this and do that. And you can leverage AI for that. But in the world of data engineering, is a little behind web development. And some of these challenges that I presented today are very easy to manage now with this integration of AI within the actual SQL. That's a game changer for data engineering. But look at it from the perspective of how it can change the way you do your work, because it's very similar when you start building components and so on. And the thing with web development and mobile development, because you got to build UIs are very tedious because there's so much validation and the sequence of the fields and the presentation and so on. So, but AI is a game changer for that as well. Okay, but I do thank you for joining us and everyone on YouTube as well. And I'm looking forward for everyone to join us on our next presentation. Okay. All right, Carol. Thank you. Have a great day, everyone. Okay. Bye-bye.